This is lesson 6.3, anti-differentiation by parts. We're going to see that this formula comes from the product rule. We're going to solve for unknown integrals, tabular integration, and how to work with inverse trig and logarithmic functions. Here's the product rule. The derivative of a product is the function times the derivative of the second plus the second function times the derivative of the first. We're going to isolate this function right here. And when we isolate it, it's right here. Then it'll be this expression minus this expression. We're going to take the integral of all. And when we do that, there's going to be some reductions here. And a derivative and an integral are going to cancel each other out. And that's why we get the uv. And then we have these two expressions. Okay, lipid is a mnemonic. And the mnemonic is supposed to help you decide what to substitute for. So in your first pass, always make your u the natural log. If you have an inverse, make it your u. And second is polynomials, barring, look for an exponential. And last is a trig expression. So I'm going to let u be equal to x, and dv will be equal to cosine x dx. Now remember that we have to find a du, which is going to be dx, and we have to find the antiderivative v, which is going to be sine of x. Now here's the integration by parts. U dv is equal to u times v minus the integral of v du. So if I want x cosine of x, I can replace it by saying these two times together, x sine of x minus the integral of v, and v is sine of x, and du is dx. And this is going to be x sine of x, and then this is going to be minus or plus cosine x plus c. Now you can always see if you've done it right by taking the derivative of your answer, and that's going to be, here's the product rule, x cosine x, and then plus sine of x, and then the derivative of this is minus sine of x, and the derivative constant is 0, and we get back to the integrand which we had over here. All right, here's an example where you have to repeat. We're going to let u be x squared and dv be e to the x, and we're going to get this expression. Unfortunately, this we still can't integrate. So just for this expression right here, this part right here, we are going to do it again. And when we do it again, we're going to get this expression. So we're going to take this and we're going to substitute it back into here, and we get this. All right, so let's take a look at trying to solve this differential equation. All right, so we want to find the antiderivative, and so we're going to do integration by parts. So we're going to let u be equal to lipid, remember, natural log of x, and dv will be equal to x. So du will be equal to 1 over x dx, and then v will be equal to x squared over 2. So the integral of x, natural log of x, and we're going to use the initial condition later, dx will be equal to u times v, which is x squared halves natural log of x, minus v, here's v, and du times 1 over x. That should have been there. That should have been a 2, and then dx. So this is going to be x squared halves natural log of x. Now when this reduces, that's going to be an x over 2, and x over 2 will be equal to x squared all over 4 plus c. So that'll be our y. We have solved for y, and now we want to use the initial condition, -1 equals, and our x is 1, so that's 1/2, and natural log of 1 is 0, minus, and then that's going to be x is 1, so that's 1/4 plus c. So then we get c is equal to -3/4, and now our function will be x squared over 2 natural log of x minus x squared over 4 minus 3/4. And so there we have found the solution with the initial condition given. All right, let's take a look at an integrand here that's a little bit more complex. We're going to let u be equal to e to the x and dv be equal to cosine x. When we do that, we're going to get this as our value, and notice it has a sign in there. So we're going to have to take a look at taking the integration by parts once again for this expression right here. So here's u and here's dv, and we're going to replace that. So it's going to be replaced by this expression right here. And notice that we're getting back the integrand that we had here to begin with. So we're going to bring that over to the other side and then divide by 2. So this is kind of a cyclic idea in that you do integration by parts once, you do it twice, you get your integral back again, and then you're able to evaluate it. All right, and here's a caution. If you're going to do this, make sure you allow u and dv to be the same thing. If you change them on the second time you do integration by parts, you'll just get back to what you have. You undo the process. Okay, here's tabular integration. It goes a lot faster. We did this before, but now I'm going to show you a little faster. Remember, we're letting this be our u, and if we just go ahead and take a derivative until we get 0, we have this column. And then we're going to take this is our dv, and we're just going to integrate until it matches these columns. And then we're going to take this product preceded by a plus sign, take this product minus this product plus. And you'll be able to get to that same answer that we got before without having to resubstitute as we had done. Okay, it's your turn. Go ahead and try to use tabular integration. Stop the screencast and continue when you are done. Here's the answer. All right, inverse trig and logarithmic functions. So in this example, we see our integrand is natural log of x. I don't know how to find the antiderivative of natural x, so I have to use integration by parts. So we're going to let u be equal to natural log of x, and we'll let dv be equal to dx. And when we do this, here it is right here, we get through the process and we're able to find the antiderivative. Okay, here is an opportunity for you to solve for this. So here's the differential equation. See if you can take the integral of both sides and solve. And if you go ahead and stop the screencast, and then you'll be able to see the answer once you resume. And here is the answer. Again, letting u be equal to the sine inverse of x and dv equals dx. And you can go through this process. And after you get that, you can go ahead and resubstitute your initial condition to find the particular solution. And this is the end of the screencast.